Okay, so let's talk about the extremal number of k22, which of course is the same graph as C4. Like we're talking about this graph, and this is a 4 cycle. It's just kind of twisted, right? So yeah, these are the same graph, but yeah, so we're doing the k22 here, and this is in the context of complete bipartite graphs, which we've been talking about, in general, I guess last time we showed this. And so for r equals 2, this would basically say, for r equals 2, this lower bound is pretty bad. The lower bound is like n to the 4/3, and the upper bound is n to the 3/2. So for r equals 2, we're going to show that the true answer is basically the upper bound. It's basically n to the 3/2, or it's on the order of n to the 3/2. So yeah, that's what we're going to do. And for the upper bound, this is basically just a repetition of the same upper bound that we already did in general. If you remember, we did Kováry-Sós-Terán, which showed this. We're basically going to run through the same argument again, except we're actually going to pay a little bit more attention to get the quote-unquote correct constant C in front. Last time we just showed that for general R and S, there exists some constant C, but we're going to actually find an explicit constant C for us this time. But it's the same, essentially it's the same argument. So for the upper bound, we just want to show that if G is any graph with n vertices and it doesn't contain this subgraph, then it can have at most some specific number of edges. And the number of edges we're shooting for is this number. But in general, that's what we need to do. We just need to show that if G has n vertices and doesn't have this subgraph, then you can have at most some number of edges. The way we attack this is by counting something. I'm going to count the number of triples. It's a set of 3 vertices such that we have this. And I didn't write mathematical, logical things here. I just drew a picture. This picture is just supposed to say that the edge from U to V is there, the edge from U to W is there, the edge from V to W may or may not be there. We don't really care, so I just wrote a question mark. So we're counting the number of sets of 3 vertices such that U is adjacent to V and W. That's what we're counting. And the argument goes by counting this in 2 different ways. Or maybe I shouldn't say counting, or I should say like estimating it in 2 different ways. One way is I could, for each pair of vertices V and W, I could count how many vertices U go with that pair VW. In other words, the number of vertices U that is a common neighbor of V and W. If I count it that way, each fixed V and W has at most one other vertex U. Because if there was like a U and also a U prime that was, like if U and U prime were both common neighbors of V and W, that would be a k22. That would be this picture. That would be like this. But we don't have that. So for each pair of vertices V and W, there's at most one U. So one way of counting these triples is to just say, here's the number of pairs I can choose, V and W. And each one of those pairs goes with at most one choice of u, so I'll just put a 1 here. And so this number of triples is less than or equal to that. Okay. The other way we're going to count this is by sort of focusing on u and then asking for a fixed u, how many pairs VW go with that u. So if I do it that way, for a fixed u, the number of pairs VW that go with u would be the degree of u choose 2. If I have a fixed u and I just want to know how many pairs VW go with it, the only requirement is that they both be neighbors of u, so I would have this many choices for v and w. And I'll just add that up for all u. And that's actually an exact count. There's no inequality here. This is an exact count. And then we have this inequality, which this is Jensen's inequality again. It's applied to this function. If you remember this page, it was in the notes a little while back. We're applying Jensen's inequality, which is this, and we're applying it to the function x choose, in this case it's x choose 2. There was an entirely similar step in the proof of Kováry-Sós-Turán from several days ago. It was the step where we got from here to here, where we used Jensen's inequality. So this is entirely similar to that. This is using Jensen's inequality. Maybe I'll write Jensen above. Okay, and of course the degree sum is just twice the number of edges, so we get this. And now I'm just going to mess with some inequalities. So this one, of course, when we're doing like x choose 2, it's x times x minus 1 over 2, which is greater than or equal to x minus 1 squared over 2. So that's all I said here. This is greater than or equal to, like x is this number, so this is x minus 1 squared over 2. All right, and we put this together. So what do we know? We have this string of inequalities, but ultimately we know that this one is greater than or equal to this one. So, okay, I'm going to do some algebra here. This thing where my left finger is pointing, that's n times n minus 1 over 2. Right? I can cancel an n, and I can cancel the 2 from the bottom. And what I'm going to get if I cancel that is this will just become n minus 1. And this will become, let's see, the n will be gone and the 2 will be gone, so I'll just have this. So that's what happened here, is I took this inequality and I canceled an n and a 2. So now I'm here. And then I keep solving. I want to find the number of edges in G. So I would do the square root, and then I would add 1, and I would multiply by n, and I would divide by 2, and I do all that, and I get this. So what we're really interested in about this is generally it's the behavior as n grows. So after I get this bound on the number of edges in the graph, I think about it as n goes to infinity. Roughly speaking, this is about 1/2 n to the 3 halves, because well, okay, I'll say this a bit informally. The square root of n minus 1, if n is large, that's very close to the square root of n. And if n is large, this 1 is insignificant compared to the square root of n. So this thing in parentheses is, when I look at this, I basically just see the square root of n. And so this is n over 2 times the square root of n, which would be this. Now, a little bit more formally, when I write this tilde thing, this is used to basically indicate that as n goes to infinity, the ratio of this over this goes to 1. And that's something you can show using calculus, using like L'Hopital's rule and that type of stuff. If you do the limit of this divided by this, you will get 1. So that's what this symbol means. Okay, so we have an upper bound on the number of edges in any graph that doesn't have k22 in it. So this is an upper bound on the extremal number. Now, I'm going to get a lower bound on the extremal number, and we're going to see that it's essentially the same. We're going to see that as n goes to infinity, it's the lower bound and the upper bound are both essentially this, which is a rare success, a rare victory in the subject of extremal graph theory. So let's see it. So what, like the lower bounds for these are, maybe there's more art and creativity that goes into them. The lower bound that we did last time was, well, in my opinion, the probabilistic method is ingenious and beautiful and all of that good stuff. But one could also very fairly say that it was an uninspired, it was not a very, like, the inspiration behind the construction was not very much. All we did is we made a random graph, and then it might have had some k sub r's in it, but we just removed some edges until they were gone. And there's just something incredibly, it seems too simple. And it didn't do a very good job either. That's the argument that basically got us to here, where we have a lower bound and an upper bound where the powers of n don't even match. We have a smaller power of n and a bigger power of n here. To do better than that, we need some inspiration. We need some structure. And I'm being very vague here, but the constructions that are more successful in extremal graph theory tend to be algebraic, meaning they're relying on some algebraic properties to construct a graph, and often the vertices of your graph will be members of a field or something like that. And the edges of the graph will be defined according to whether the vertices satisfy some equation in the field. Meaning, so that's what I mean by an algebraic construction. So more specifically for us right now, choose a prime number p, and let's assume that n is p squared. We can talk about values of n that are not the square of a prime later, but for right now, let's assume that n is the square of a prime. So I'm going to define a graph. The vertex set of the graph is going to be zp cross zp. So the vertices look like this. They're pairs, where x is a member of zp and y is a member of zp. And we have one vertex that's denoted by such a pair, and that would be adjacent to another vertex, and say the other vertex is denoted by this other pair. And these two vertices are adjacent if they satisfy this equation. And the claim is that this graph is essentially just what the doctor ordered. In other words, this graph, first of all, does not have k22 as a subgraph. And also it has a number of edges that essentially matches the upper bound that we proved. That's saying that you can't have more than this many edges without containing a k22. We're going to show that it has almost that number of edges. Okay. Each vertex has at least p-1 neighbors. That's because, say, if you fix x and y, and then asking how many neighbors is like asking how many other pairs x prime, y prime are there that satisfy this equation. And it's fairly easy to see that if x and y are fixed, then basically what I can do is I can run through every possible value of y prime. And for each value of y prime, there's going to be a unique x prime, right? You can just solve this equation for x prime. X prime is that minus x. And if x and y are fixed, then you can just run through each possibility for y prime, and each value of y prime corresponds to exactly one value of x prime. So, right, you would think that means I just showed that this has p neighbors because there's p possible values for y prime. Of course, right. There, yeah, let me try to explain this a little bit better. There's one possible thing that's why I'm writing p-1 instead of p. So I'm talking about going through this and plugging in every possible y prime. It's possible that I would get the same solution back, meaning it's possible that if I do y prime equals y and I solve for x prime, the solution that I get is x prime equals x. I mean, if it's the case that 2x equals y squared, then that's what would happen. Like when I'm running through all the possibilities for y prime and I get to this possibility, it's possible that when I plug that in and I solve for x prime, that I get x prime equals x. In other words, I'm just showing that like xy and xy satisfies this. But we're talking about a graph, and we wouldn't say that a vertex is adjacent to itself. So I'm not going to say that the vertex xy is adjacent to itself. So it's possible that this happens, but that's just one of the solutions. So it's possible that out of the p possible values for y prime, it's possible that one of them doesn't really count. That's why I say p-1. Anyway, xy has at least p-1 neighbors. So the degree of each vertex is at least p-1. So I can count the number of edges. Of course, the number of edges is half the degree sum. And if I do half the degree sum, let's see, here's half. There are p squared many vertices, and each vertex has at least degree this. So the half the degree sum is greater than or equal to this. And when I convert this back into n, because n is p squared, this is 1/2 times n times the square root of n minus 1. And this is essentially 1/2 n to the 3/2. I use this symbol again. You can show using calculus that if you do the ratio of this divided by this, it does go to 1. So the number of edges in this graph is essentially 1/2 n to the 3/2. The other part I still have to justify is that this graph does not contain k22. So, right, what we're going to do is I'm going to fix two distinct vertices, x1, y1, and x2, y2. Like this. And then I'm going to show that they can't have two common neighbors, because that's really what a k22 looks like. It's like you have two vertices and they have two common neighbors. So fix two vertices, x1, y1, and x2, y2, and then let's talk about what a common neighbor would have to look like. If x prime, y prime is a common neighbor, then that means x prime, y prime satisfies this equation in order to be a neighbor of x1, y1, and also satisfies this equation in order to be a neighbor of x2, y2. But now we have a system, and we can solve this. So I can just subtract. We have to be careful not to do anything that's invalid in ZP, because we're doing algebra in ZP here. But if I just subtract the equations, I'm going to get this. And this has at most one solution. I guess let's talk about this for just a second. Of course, there's a little bit of danger here. Like, okay. What am I talking about when I get to this? This would have, as long as y1 minus y2 is not 0, this would have a unique solution for y prime, and then I would plug that solution in for y prime, and I would get a unique solution for x prime. What happens if this is 0? Well, if this is 0 and this on the left is not 0, then there's no solution for y prime, which is fine. We're just saying that there's at most one solution. If this is 0 and this is 0, then that means these two pairs weren't actually distinct. That means x1 is the same as x2 and y1 is the same as y2. But we wanted to choose two distinct vertices. So these aren't both 0. So in any case, there is always at most one solution for y prime, and then you would plug that in and get one solution for x prime. In other words, these two vertices can have at most one common neighbor. They cannot have two common neighbors. Two common neighbors would be two solutions to the system. So there we have it. We have a graph that does not contain k22, and it has about this many edges, which we showed previously. A graph without k22 can't possibly have more than roughly this many edges. So, right. Now, yeah, so now would be the time for me to discuss the distribution of primes. Of course, everything that we just did is only valid if n is the square of a prime. And, right, so there gets to be this strange interplay between number theory and extremal combinatorics, but we don't really want to talk too much about number theory. We're just going to sort of use and abuse some basic results. So, right, primes are frequent enough that basically you can use the squares of primes as like fence posts, and if you give me a value of n that is not the square of a prime, I can just find the nearest square of a prime that's less than that value of n, and that will be fairly close. That will be close enough to n where if I just use the bound that this gives, it will still essentially be 1/2 n to the 3/2. And I'm officially being hand wavy at this point, but the fact, so roughly speaking, the fact that this argument requires n to be the square of a prime does not essentially affect the result. The extremal number of n and k22 is still, like, if you do the ratio of that to 1/2 n to the 3/2, it still goes to 1. Primes are frequent enough for this to work. So yeah, that's the extremal number of k22 then.